Welcome back, Physical Science 20. This is the beginning of the HT1.4, States of Matter and Changes in State. This will likely take a couple of videos. We'll look at the first part with this video, then we'll look at the second part in the following video or videos. So construct a heating or cooling curve for water or other substances using personally collected data and appropriate graphing techniques. I'll give you some data and we'll be able to do that. Calculate the quantity of heat, Q equals MC delta T like we were before, plus the latent heat of fusion and the latent heat of vaporization during changes in state. That'll be more in the next video. And this last part too, the anomalous properties of water, that'll be in the next video as well. So first of all, states of matter. Water and all forms of matter can exist in three physical states: solid, liquid, and gas. The kinetic molecular theory, and remember that kinetic means moving, so the moving molecule theory described earlier explains the differences between these physical states. In a solid, strong forces of attraction hold the particles in fixed positions. The particles do vibrate though, so they're very close together as seen here, but they are capable of moving a little bit, in other words, vibrating. This gives solids their rigidity and allows them to maintain their shape. The particles of a liquid are also attracted to each other, but however in liquids the particles have more moving energy than particles of a solid. This causes them to vibrate more than the particles of solid and allow them to slide past each other. And as you can see here, they're further apart from each other. Like solid, this gives liquids the ability to flow. Like solids and liquids, particles of gas are also attracted to each other. However, particles have even more kinetic energy or moving energy than solids and liquids. The particles of a gas vibrate more vigorously than particles of a solid and liquid, and they move large distances past each other. So it has to do with how close they are to each other. So gases are further apart, and they can expand and fill their containers. Changes of state. When a solid, liquid, or gas absorbs or releases thermal energy, they may change state, as seen in the figure on the right. So if you absorb energy, you go from solid to liquid to gas, because you're allowed to move quicker and quicker, spread further apart. But if you release energy, you slow down, get closer together. Okay? So when you absorb thermal energy, so when a substance absorbs, the particles of a substance begin to move faster and farther apart when things are absorbed. Note that the thermal energy is not really absorbed. It is transformed into kinetic energy and potential energy of the substance's particles. Remember that energy is always conserved. It can be transformed from one form to another, but not created or destroyed. Okay, this next part here goes through an example of just simply looking at water, for example, starting from a solid, liquid, to gas. So let's consider what happens when you have ice initially at -10. So of course at -10, water would be in the solid state, right? When it is continuously heated, when the ice is placed on the hot plate, its initial temperature is -10. As ice absorbs thermal energy, its particles begin to vibrate more and more. This warms the ice and increases its temperature. As the particles absorb more thermal energy, the forces of attraction are not strong enough to hold it in fixed positions. Eventually, the solid reaches the melting point, where the particles begin to move past each other and move from place to place. At this point, the solid begins to change to a liquid. The melting point of water is 0 degrees C. The change of state is called melting, or sometimes we refer to that as fusion. Eventually, all the ice becomes liquid water. Notice that thermal energy continues to be absorbed during the melting process, but the temperature does not change. So what happens here is when ice, so the temperature increases, it's absorbing energy, then it stays at 0 for a while. And notice you'll see ice, you still see ice, but once all the ice is gone, then the temperature starts to move up. So why that happens is that as the liquid water continues to absorb thermal energy, its particles move faster and farther apart. This warms up the liquid and increases its temperature. As the speed of the particles increases, the force of attraction becomes weaker, and it becomes more difficult for the particles to stay together in a liquid. Eventually, the liquid reaches what is referred to as the boiling point, at which particles have enough kinetic energy to completely break away from each other. At the boiling point, the liquid water changes into a gas and called water vapor, and that occurs at 100 degrees C. That change of state is called evaporation or vaporization. Eventually, all the liquid goes into a gas. Again, notice that at the just like at the melting point, at the boiling point, energy is continually being added, but it doesn't change for a while until all the liquid becomes vapor. It remains at 100 degrees C until the last drop of water is changed into vapor. Changes of state occur whenever any material is heated from solid to liquid to gas. The only difference is that every material will have a different melting point and boiling point. So for example, water melts at 0 and boils at 100. Different materials have different points at which that happens. If we do vice versa, removal of thermal energy reverses the process. In the case of a gas, it cools down into a liquid, then cools down into a solid. The change of gas into a liquid is called condensation, so vice versa. And the change of liquid to a solid is called freezing. In some cases, it's possible for a substance to go directly from a solid to a gas, or vice versa without becoming liquid. That special case is called sublimation when we skip that phase. An example of sublimation: when ice cubes are kept in the freezer for a long period of time, the ice becomes smaller and smaller as they sublimate into water vapor. Now, I think we drew this diagram before here, but if you kind of think of it, solid, liquid, gas, so melting, and then we have freezing going in this direction. Vaporization or evaporization, yes. And then condensation. That should be one word, but it's falling off your paper there. Okay? So heating, if we were to graph that information now, heating and cooling graphs, the changes in temperature that occur when a substance absorbs thermal energy can be shown in a graph called a heating graph. So if you're absorbing thermal energy, things are getting heated up. Similarly, the changes in temperature that occur when a substance releases energy is shown on a cooling graph. In both graphs, the y-axis is the temperature and the horizontal axis is the amount of thermal energy absorbed or released. Figure below shows a heating graph, figure B shows a cooling graph. So if you take a look here, again, if we're starting off with that water, it's starting off at -10, heats up until it reaches 0. Then it's melting, temperature stays at 0. Once all that ice has melted, gone from a solid to liquid, then the temperature goes up when it's a liquid, then again, it stays at a constant 100 degrees C in this case, while it's evaporating. Then once it's all a gas, then it heats up again. And vice versa happens for the reverse process. Cooling a gas down, cooling a gas. As the gas is changing to a liquid, it's going at the condensing temperature, which is also 100 degrees C. Once it's all liquid, then it lowers down in temperature until it's changing into a solid. It stays constant at 0, and then it eventually freezes. So some key areas to note on that graph. On the heating graph, thermal energy is being absorbed as it's being heated. On the cooling graph, thermal energy is being released. So cooling, energy released; heating, energy absorbed. Temperature changes occur only when one state is present. Okay, so that's one thing that we can note there too. So if we go back to here, we could say, okay, well, here we have solid. Maybe let's just use I'll do it like this. Liquid, gas, liquid, solid. And of course, in here we have S going to L, solid going to liquid. Here we have liquid going to gas. So we can write that phase in there. Here we have gas changing into a liquid. And here we have a liquid changing into a solid. So you can label those parts there. Okay, what we'll do is we'll come back and we'll do part 2 of this video and continue on with this section.